So in the last video, we defined a composition of n into k parts as a sum of natural numbers, of k different natural numbers that add up to n. And C of nk just tells you how many different compositions of n there are into k many parts. So I asked you to look at exercise 2, which asks you to fill in the table where you're trying to find C of 6, k for various values of k. Right, so we're trying to list out all the different compositions of 6 into 1 part, or 2 parts, or 3 parts, or 4 parts, etc. Okay, now this starts off pretty easy. The number of compositions of 6 into 1 part, I mean, if you're going to have a sum of numbers that add up to 6 and it only has 1 part, there's only one composition, and that's just the number 6. So there's just one single composition there. Into 2 parts, this gets bigger, right? Because we had done this example in the last video. You could have 5 plus 1, or 4 plus 2, or 3 plus 3, or 2 plus 4, or 1 plus 5. So there's a total of 5 compositions of 6 into 2 parts. What about the compositions of 6 into 3 parts? This gets even more complicated. We could list them all. It would be 4 plus 1 plus 1, or I'm going to just do 1 plus 4 plus 1, or 1 plus 1 plus 4. Just to get those 3 different, it's sort of the same numbers but in a different order. That gives us 3 different compositions, or we could do 3 plus 2 plus 1, or we could rearrange this in 6 different ways, right? 6 permutations of those 3 numbers. I don't want to list them all out. So that's going to give you 6 more permutation, or 6 more compositions, and then finally for the last one we could do 2 plus 2 plus 2. So that's a total of 6, 7, 8, 9, 10 compositions into 3 parts. 4 parts, let's skip it for now. 5 parts seems like it might be messy, but it's actually not that bad, because if you want to have a composition of 6 into 5 parts, most of your parts are going to have to be 1. You can either do 2 plus 1 plus 1 plus 1 plus 1, 2, 3, 4, 5, 6, or you can move the 2 over here and do 1 plus 2 plus 1 plus 1 plus 1, or you can move the 2 here, or here, or here. So this is going to be also a total of 5 compositions. And the only composition of 6 into 6 parts is if every part is a 1, so there's only one such composition there. And I can tell you that for 4, that's also a 10. Now, looking at this table here, hopefully these numbers look familiar, right? They should look familiar. This is just the 5th row of Pascal's triangle. And we know that this 1 is the same as 5 choose 0. 5 is the same as 5 choose 1. 10 would be 5 choose 2. 10 would be 5 choose 3. 5 choose 4. And finally 5 choose 5. Which suggests to us that possibly the number of combinations of 6 into k pieces is going to be given by 5 choose whatever your k is minus 1, right? 2 minus 1 is 1, 3 minus 1 is 2. Why is that though? Well, to prove that this formula makes sense and to generalize it to any n, we need to use something called a stars and bars method. And this is actually a lot like what we were doing in the warm-up problems, except now there's stars instead of circles, right? So they call it stars and bars because we usually draw stars to represent the objects being divided up. So the stars and bars method basically says you have n many stars and you're trying to divide it up into a composition. So you need to place some number of bars to divide this up into pieces. So let's do this for a specific n and k. I've already drawn 1, 2, 3, 4, 5, 6, 7, 8 stars. And let's say I wanted to count the number of compositions of 8 into 6 pieces. If I want to divide these into 6 groups, I'm going to have to place exactly 5 dividers. Right, if I place 5 dividers, let's say 1, 2, 3, 4, 5, then I've broken up my stars into 6 groups. The first one is a 1, second one is a 1, the third one has 2, then 1, then 2, then 1. So every placement of 5 dividers is going to give you a unique composition. And the question is, how many ways can I choose to place those 5 dividers? Well, just like in those warm-up problems, you have a space in between every pair of stars. And so if you have a total of 8 stars, then that means you have 7 spots in between the stars. So here's the first one. So you could place a divider here, or you could place a divider here, 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 here. Right, there's 8 stars, but that means there's only 7 spaces in between the stars. So you have 7 places where you could place a divider. And you need to choose exactly 5 of those. You need to choose 5 spots. So of course there's 7 choose 5 ways to do this. And we use 7 and 5 here so that we could actually draw a picture, but there's nothing special about that. This works for any n and k as long as k is less than or equal to n. So that leads us to our theorem here, that we can compute the number of compositions of n into k places using the formula n minus 1 choose k minus 1, as long as n and k are natural numbers with k less than or equal to n. And the proof of that is really just the same argument we gave on the last page, but using n's and k's instead. So any composition of n into k parts can be represented by placing k minus 1 dividers in the gaps between n stars. Right? If you want k pieces, you only need k minus 1 dividers. How many gaps do you have? Well, since there are n stars, there are only n minus 1 gaps between the stars. So you have n minus 1 gaps to choose from. You need to choose k minus 1 of them. So there are n minus 1 choose k minus 1 ways to make this choice. And that's it for this proof. Simple enough. This is a little bit more tricky if you change the rules and you say we're allowing for some of our groups to have 0 in it, but you'll see in the solutions to warm up 2b, there's a problem similar to that. This actually leads us to kind of a nice corollary though, because if we go back to our specific example when n was equal to 6, we found the total number of compositions of 6 by breaking it up into pieces. We looked into the compositions of 6 into 1 part, or 2, or 3, all the way up to 6 parts. You couldn't have any less than 1 part, and you couldn't have any more than 6 parts. So this total number of compositions, when you add it all together, is going to be your C of 6. C of 6 is just the total number of compositions into any number of parts. So it's 1 plus 5 plus 10 plus 10 plus 5 plus 1. But this is just a 5th row of Pascal's triangle, and we know that when we add it up together, we end up getting 2 to the 5th power. Right, 2032, which is 2 to the 5th power. That's going to be true in general because we know that the number of compositions of n is just going to be, well, it has to be the compositions of n into 1 part, plus the compositions of n into 2 parts, plus the compositions of n into 3 parts, all the way up until the number of compositions of n into n parts. Right? Any composition is going to have between 1 and n parts to it. Using that theorem up above, the number of compositions of n into 1 part would be n minus 1 choose 0. Compositions of n into 2 parts would be n minus 1 choose 2 minus 1, which is 1. Compositions of n into 3 parts would be n minus 1 choose 3 minus 1, all the way down the line until you get to n minus 1 choose n minus 1. This is the sum of the n minus 1st row of Pascal's triangle, and we know that this is equal to 2 to the n minus 1. So the total number of compositions of n into any number of parts would be 2 to the n minus 1. And that follows from what we've learned in the binomial theorem. Okay, so try the rest of the exercises from section 2.5.